Hey, it's Mr. K doing a video for AP Physics 1 and 2. This is a lead-in to Electrostatics for AP Physics 2. 2 will get a lot more in-depth than this, but this is a very good intro, I think. Let's go ahead and talk about electric charges. You should know from prior classes that we have two different types of electric charges, positive and negative. And if we have a positive charge here, that's going to be due to protons. If we have negative charges, that will be due to electrons. Initially, we didn't know which was which, and that's going to lead into the direction of current flow when we go into circuits. So Benjamin Franklin, he didn't know whether the electrons or the protons were the things moving, and he just said that the protons were moving, but we later on found out that the electrons actually were. And so electrons are going to be on the outside of your atom. Usually you draw the atom with the protons in the middle. And if there's only one proton, we're talking about a hydrogen atom there. But these electrons are like 10,000 times the distance away from the center of the atom as the size of the nucleus. So imagine we have like a golf ball, and 10,000 times the size of the golf ball is going to be how big that electron cloud is, which is huge. Put it on the scale of maybe like you got a golf ball and they say like 1 kilometer away would be where those electrons would be if the golf ball was that proton. So these atoms are mostly empty space. And there were many experiments that led to this understanding that, yeah, the atom is actually pretty much empty. And we will talk about more of that when we get to nuclear reactions and quantum. But let's just stick around here. Got a proton there. The proton is, these may or may not be useful to you, but the mass of the proton is going to be 1.67 times 10 to the negative 27 kilograms. It's also got a charge. The charge, we're going to use the letter Q. It's going to be a plus Q charge of, let's see, 1.6 times 10 to the negative 19th. And it's going to be the charge unit is going to be the Coulomb, so that's going to be the C. Do not mix this up with E equals mc squared. That C is going to be the speed of light. So this is going to be coulombs of charge, 1.6 times 10 to the negative 19th. We also have negative charges here, which we can talk about as well. I'm going to put a negative charge. Although I draw it the same size, it's going to be definitely different in mass. The mass for an electron is going to be 9.11 times 10 to the negative 31. So if you notice about the size difference here, we've got times 10 to the negative 27, we've got times 10 to the negative 31. How many zeros is that? That's like 4 zeros. So that's huge on the amount of difference in mass of the proton and the electron. However, the charge on the electron is going to be the exact same number, except it's going to be negative. So 1.6 times 10 to the negative 19th coulombs of charge. So we've got positive charges, we have negative charges. We found out that negative charges were actually the ones that were able to be plucked off and moved around, given that you have enough energy to do that with them. If not, they are just going to be orbiting in this cloud. They're moving really fast, and you really can't tell where they are. And they're moving so fast that the picture of the atom that you would usually see, it's actually more like a ball, all right, because you don't know where these electrons are. And so when we talk about charges, we're going to talk about either positive charges or negative charges, and the symbol for the charge is going to be the Q. So if we talk about positive charges, let me go ahead and separate these for right now. Let's put this right here. So if we talk about positive charges are going to attract negative charges. You've heard of opposites attracting. That's true. Negative charges will attract positive charges. The positive charges, though, will also repel other positive charges. They don't like to be near each other, which is kind of weird because the protons and nucleus of an atom are all next to each other, and they're held together by what's called the strong force. So it's a super strong force, but it acts over a very short distance. On general, though, positive charges want to get away from other positive charges. Negative charges want to get away from other negative charges, but they definitely want to attract the opposite thing. And so what we have here are two charges, and there's going to be a force between them. Much like how we have two masses and gravity, gravity will bring two masses together if they're just sitting out in space. And so if we have a positive charge and a negative charge, then we should have a force on either charge. The positive will be going to the right for a force, and the negative will be going to the left as far as that force is concerned. And then the question would be, who has the greater amount of force? And so this is a conceptual question that you have to answer. Who has more force on it, the positive charge or the negative charge? And the answer to that would be, it's the same force. because of Newton's third law, one force doesn't exist without the other, and these are the equal and opposite reactions, and notice how they're on opposite acting bodies. So these two forces are equal and opposite, they act on the other thing. The negative is causing this force of attraction over here, the positive is causing the force of attraction over there. It's the exact same force but acting on different things. Now what is different would be the acceleration, because don't forget, F is still equal to ma, and if the forces are the same, well, the masses definitely aren't the same, so the electron's going to be the one with a lot of acceleration, and the proton's going to be the one with very little acceleration, comparatively speaking. So now the big question is, how the heck do you figure out the force? Well, this guy named Coulomb, and Coulomb's law, if you are in AP chemistry, you've probably already talked about Coulomb's law, or if you are in pre-AP chemistry, you might have heard of it. But Coulomb's law is the force of attraction between two charges, either positives or negatives. And that force of attraction is K Q1 Q2 divided by R squared. This should look really, really familiar. This is the same setup as G big M or M1 M2 divided by R squared. This is the attraction of gravity of two masses. And so the setup is exactly the same, but the big difference here is that the force of attraction between charges is not going to use mass, it's going to use the amount of charge. So the Q1, Q2, charge 1, charge 2. Alright, R is going to be distance, it's squared, so it gets weaker to the inverse square, just like how gravity does. And then the other big difference is going to be this G or this K. While G, big G, is a universal gravitational constant, and that's going to be 6.67 times 10 to the negative 11th Newton meters squared over kilogram squared, just so that our units cancel out whenever we multiply them all together. K is going to be 9 times 10 to the 9th Newton meters squared over Coulomb squared. And again, we need those units to cancel out to leave us only the newtons when we work this equation. If you notice, times 10 to the 9 and times 10 to the negative 11, there's a big difference there. And it's an extraordinarily amount of zeros difference. And that shows you that the electrostatic force is way, way, way stronger than the gravitational force. In fact, in class, I would be able to move things with my hand if I was charged up due to the electrostatic force, whereas for gravity, you need an entire planet to really have that good effect on it. So, same setup, but very, very different as far as the strength goes. Now, if we wanted to figure out the force of attraction between these two, we would have to know how far away one was compared to the other. And let's just say that these two are only, let's say they're only 1 meter apart, okay? And if they're only 1 meter apart, then the positive charge will definitely be attracted to the negative charge, and the negative charge will definitely be attracted to the positive charge. And we can figure out the force of attraction by doing the Coulomb's law equation. K, which is going to be 9 times 10 to the 9th, Q1, which is going to be 1.6 times 10 to the negative 19, Q2 is going to be the other guy, 1.6 times 10 to the negative 19. I'm not going to put the negative there because I know which way the force is going to act on either object that's drawn. And then we're going to divide that by the distance between them, and the distance we chose is a very simple distance. It's going to be 1, and we're going to square it. All right. So the key here is to set it up just like the gravitational force equation, and we're going to see the force of attraction between these two. 9 times 10 to the 9, and that's going to be multiplied by 1.6 times 10 to the negative 19th, and we're going to hit enter again to do it again. So the force of attraction is going to be 2.304 times 10 to the negative 28 newtons. Okay? Now, that seems super small, but you got to think about the objects that are interacting here. So to the negative 20, actually negative 28, did I say 27? 28. So to the negative 28, this mass is times 10 to the negative 27. That's still going to provide a decent amount of acceleration to this proton. And then think about this electron. This electron is times 10 to the negative 31. That's going to provide a crap ton of acceleration to this electron. You know, so although these are a meter apart and they're only a proton and an electron, there's going to be a huge amount of acceleration on this electron here. And so that brings us to the next topic of, you know, why would this electron feel the force in the first place? And so what we need to do is we need to take the electron away. And so I'll draw another scenario down here where I'm only going to have a proton. So if I only have a proton sitting in space, or just a positive charge sitting in space, let's just say that, what would happen if I brought another positive charge near it? And so if I had something, let's say like this binder clip here, if I had this binder clip and I placed it right here, well, there are a series of things that could happen to this binder clip. One, if this binder clip was made of positive and negative charges, the positive charges would be pushed away and the negative charges would be attracted too. And so the negative charges, being those electrons, are going to be able to shift over to the left a little bit, getting a little bit closer to this positive charge in space here. The negative charges would have left behind their positive charges over on the right side, and they would be pushed away from this positive charge here. And because of that shifting of the charge, a little bit more force would be attractive than repulsive, and this binder clip would be drawn towards this positive charge sitting in space, just as it would be drawn towards this binder clip a little bit. So that's called induction of charge. We're going to induce a charge that way. But let's say, what if this binder clip was positively charged? If I placed it here, what would happen to it? Well, if I have a positively charged binder clip and I just placed it right here, positive charge, they would repel. If I have this binder clip and I placed it over here, well, they would still repel. If I placed it up here, they would still repel. So wherever I place this binder clip would be repelled if it was positively charged by this positive charge sitting in space. And that's because I'm placing it in what's called an electric field. So the electric field for positive charges is going to point outwards in all directions. Okay, it's going to point up, it's going to point down, it's going to point towards us, it's going to point away from us, it's going to point to the right, it's going to point to the left. And it's going to get weaker to the inverse square, much like gravity does. And so to go through, I'm just going to draw these. I'm not going to draw all of them because that's impossible. But we have up, down, left, right, we've got diagonals, we've got all these different directions for our electric field. And so the electric field here, again, for positive charges, for a point charge in space, it's going to look like that, just all directions, all outwards. But it's going to get weaker to the inverse square. And so the way that we can figure out the electric field strength is we would take, again, that K value, that 9 times 10 to the 9 value that we had before, we would multiply it and use the charge that was creating this electric field and divide by r squared. And you're going to say, wait, that looks just like this other equation up here. And it does, but it's missing one thing. It's missing the charge, the other charge that would be affected by this electric field. And so a very simple thing to do is to take the force and divide it by the charge, the force on a charge divided by that charge itself, to find the strength of the field that charge is sitting in. All right? And so the other way you can do it is you can say, oh, well, I have an electric field. If I do, I can put a charge in it, and if I put a charge in it, then this all of a sudden becomes the force on that charge that I have just placed into that electric field. That's why I could say, hey, I've got this charge sitting here. I can place a positively charged binder clip right here, and then I would have a force on it in that direction, in the direction of the electric field. Okay? If I had instead not a positive charge, but maybe a negative charge, and I placed it there, then I would have a force of attraction, which would be the electric field strength at this location times the charge that I just placed there. All right, or you can work the whole KQQ over r squared equation. As you get more familiar with this, it's going to make a lot more sense. It's kind of like with this gravitational force equation, I could have the planet Earth, and all around it we have this gravitational field. And we know that it exists, right? It's right in front of us all the time. It's right behind us. It's right below us. It's right above us. But until we place something in it, we don't have to worry about the force that it creates. Okay, so we have this positive charge. What about a negative charge? All right, if we have a negative charge sitting in space, that negative charge is going to have that same kind of electric field. However, let's see if I can switch over my colors here. That negative charge is going to have electric fields that are going to go not away from it, but towards it. Okay, so all we're going to do is we're going to flip the direction of that field. And fields are vectors. So, wow, this is really dying out pen. I actually haven't used it in a while. So, we can have this electric field going towards this charge in all locations. And it's a vector. And what can we do with vectors? Well, if you are a good physics student, you would say, well, vectors can be added together, right, Mr. K? And I'd say, well, yes, very good physics student. Vectors can be added together, which means that you can cancel them out as well. So if we are going to look at these two charges, and they're creating their own fields, if I were to pick a spot, let's say like right in the middle, this is right in the middle. If I were to pick a spot like right in the middle between those two charges, I can figure out what the electric field is going to look like there. And if I can do that, it looks like I have an electric field due to this red one that points to the left. I have an electric field due to the blue one that points to the left, which means in the middle, the electric field should point to the left. All right? And all that says is, yeah, let's take a positive charge. Let's take our positive binder clip. If we put it right in the middle, would it feel a force? I got a positive charge there. It's going to feel a force that way. I got a negative charge there. It's going to feel a force that way. And so this binder clip that's positively charged would feel a force to the left based on being pulled towards the negative charge and pushed away from that positive charge. And so my electric field will point to the left. What about up here? Okay. And if we go up here, I know that I have an electric field that points directly away from this positive charge. It's going to go somewhere in that direction. But I have a negative charge here, and I should have an electric field that points straight towards it. And what can vectors do? Well, they can add together. So these two electric field lines are going to add together, and it's going to point to the left if I'm in this location here. If I'm down here, it's also going to point to the left. And what ends up happening is we've got these field lines that start to go from one charge to the other, and they're going to point over to this negative charge. And I love how these brand new pens are dying already for some reason. I gotta figure out what's going on with that. And so these electric field lines are going to go towards and point towards the negative charge, while they're going to point away from the positive charge. Okay, and in the very middle they're going to still point like that. All right, and what all this says is that if you place a positive charge anywhere in this electric field, you're going to feel a force, and it's going to be in the direction of that electric field itself. So let's do a little problem of some charges and try to figure out what the electric field is like, what the force is like on some charge between two charges. So I'm going to put a charge here. I'm going to use a 2 microcoulomb charge, micro being times 10 to the negative 6. I'm going to put another charge 1, 2, 3, 4 away from it. Let's say right here. And let's make it another positive charge. And this will be a 4 microcoulomb charge. And let's put another one 1, 2 away from it here. And so let's make that a negative charge. And that's also make that just a 2 microcoulomb charge, but it's going to be negative. And so just a quick practice problem. What's going to happen to this 4 microcoulomb charge, when we say go? And if we say go and this 4 microcoulomb charge is just sitting here, it's going to feel a force of attraction to this negative charge to the right. It's going to feel a force of repulsion from this positive charge to the left. And so where this negative 4 microcoulomb charge is, it's going to have a force on it to the right. It's going to have another force on it to the right. Okay? It's going to have 2 forces on it to the right. And those 2 forces should add together to say, hey, we got an overall force to the right due to these 2 charges out here. So let's see what those forces are. We've got this first force, which is going to be K, Q1, which is going to be, let's call this Q1, let's call this Q2, and let's call this Q3. And so our Coulomb's law, our forces between these charges are going to be K, Q1, Q2, these 2, over R squared. And we didn't really define an R. Let's just use these squares here. So 1, 2, 3, 4. That's going to be 4 meters. And this is going to be 1, 2, 3, or 1, 2. That'll be 2 meters. And so we have a first force of repulsion between these 2 charges at this 4 meter distance. We are also going to have to add to that the other force of attraction, because it's in the exact same direction. Got to use some vector math if it's not in the exact same direction. But here it is. So K, Q2, and then Q3 divided by this other r, let's call this r1 and r2 squared. All right, and this should equal our overall force. All right, so let's see, can we extract anything out here? We got a k on both things, we got a q2 on both things, so I can take the k out, and so I'm going to say k, q2's out here, and we've left behind q1, and let's see, q1 was 2 times 10 to the negative 6, r1 is going to be 4, and it's going to be squared. Add it to, I would have taken out this q2 and this k as well, so it's going to be q3, and that's going to be 2 times 10 to the negative 6. And again, I'm going to ignore this negative sign here because we know which way the force is going to be. And we're going to divide this by 2, and we're going to square that. Okay, so let's just get a good number for whatever we have in the parentheses, and then we'll multiply it by this stuff out here, that stuff being 9 times 10 to the 9th and 4 times 10 to the negative 6. So 2 times 10 to the negative 6 divided by 16. You know what, let me go to scientific. There you go. That's going to be 1.25 times 10 to the negative 7. We're going to add that to 2 times 10 to the negative 6 divided by 2 times 6 is 4. And so that's going to be 5 times 10 to the negative 7. If we have times 10 to the negative 7 times 10 to the negative 7, we just add these 1.25 to the 5. That's going to be 6.25. And so I have 6.25 times 10 to the negative 7 in the parentheses. Outside the parentheses, we have 4 times 10 to the negative 6. And then we've got a 9 times 10 to the 9. Let's do this math right quick. So take that value there, 6.25 times 10 to the negative 7, multiply it by 4 times 10 to the negative 6, multiply that by 9 times 10 to the 9, and I get a value of 2.25 times 10 to the negative 2 newtons. And you're going to say, hey, that's really, really small. But again, remember, we're working with really, really, really tiny masses. We can probably figure out how much mass there is there by the actual charge on it, because this is all made up of protons, to find the acceleration. The last thing that we could probably do here, actually two things we can do, but I'm going to stick to this one last thing with the field, is we can say, all right, you got a force in this guy, it's to the right. What if you didn't have anything there? If you didn't have anything there in the first place, there's a field there, and the field would point to the right, okay? And if you place the charge there, it will feel the force. So how strong is the field at that location? And that's the question that we need to answer. Well, going back to the very beginning, we talked about electric field and electric force. We talked about this equation up here. These equations look very, very, very similar. And all we need to do is take the force divided by the charge being affected by that force, and we should get the field that that charge is in. And it just so happens that we just found the force on that charge. So 2.25 times 10 to the negative 2. We're going to divide that out by the charge that we placed there. It's going to be 4 times 10 to the negative 6. Okay, and so we can find the electric field strength. So 2.25 times 10 to the negative 2, divide that by 4 times 10 to the negative 6, and that's going to give me a electric field strength of 5, let's see, times 10 to the third, 5,625, and the unit here is going to be newtons per coulomb. All right, and that just says the amount of force per coulomb of charge that we place in. Yeah, that's a huge number, but electric fields are going to be very, very, very strong, or high numbers, whereas the charges that you place in them are usually very, very, very small. So those exponents usually cancel out to something reasonable in size. So I'm going to stop this video here. This is just a basic introduction to Coulomb's law. Charges that you have probably already heard of, positives and negatives, will attract or repel depending upon the types, and the equation for that attraction or repulsion is going to be the Coulomb's force equation, KQQ over R squared, K being this weird number here. There's another way to get it, but that's more of an AP2 level thing called Gauss's law. So we'll stop there. All right.